So in 9.2, we're still working with confidence intervals, but we're changing gears a little bit. Instead of our survey question being a yes-no question where we're doing proportions, what proportion or percentage of people like chocolate chip cookies, what proportion of people like to show friends. Instead of a yes-no question, our question is going to be a numerical, and we're going to be interested in finding the mean from the different survey respondents. So maybe we ask them, how many credit hours are you taking this semester? Okay. How many kids do you have? How much do you make per hour at your job? Okay. And so those answers that we get from people will be numbers. Now, let's say we ask them for, hey, how much do you make per hour at your job? Well, people that aren't working would probably say, oh, zero. I make $0 an hour. Other people might say, oh, I make $12 an hour. Oh, I make $10.75 an hour. Oh, I make $13.80 an hour. Whatever it is. Okay. So we take all the responses that we get and average them together, get our mean, okay? That mean, since we did a sample, the symbol for that is X bar. So let's say the average person in our survey made $11.50 an hour. Our X bar would be $11.50. That was the average salary, okay? Our concern is, okay, well, how does that $11.50 match up to the entire population of all people, okay, or specifically college students? We just surveyed a few college students. We would like to know, hey, does that match the entire population mean, all college students' average salary, okay? Now, in theory, if we've done a good job, that $11.50 ought to be fairly close to the population mean, the mu. But it's probably not an exact match, okay? So we would build a confidence interval to say, well, it's probably between this and this, okay? Remember, when you do a confidence interval, your point estimate is the number in the middle. That's the number in the middle, and then you add a little bit to it and subtract a little bit from it to get your interval, okay, that you're creating. Your point estimate for mean is X bar. When we did proportions, we had P hat in the middle. Now we're going to have X bar in the middle because we're doing means, okay? And then we will still add and subtract our E, our margin of error. Okay, now, we mentioned in 9.1 that we were basing it off a normal distribution, okay, which is based off z-scores. When we are using means, it is not appropriate for us to use normal distributions and z-scores, okay? Reason for that is, let's say here's my whole population, all the people in my survey, and I go and I ask all, well, I can't ask all the people, because otherwise I would know the results of the entire population. It wouldn't be a sample anymore. But I might go survey these people over here, and their average salary might be $10. And then I might survey this group over here, and their average salary might be $15. And I might survey these people over here, and theirs is $9.75. And each group is going to have a different average. And that average, or mean, will definitely be different than the entire mean. So what happens is, to allow for all those differences to occur, we use something called a t-distribution, or specifically student t-distribution. It's very similar to a normal distribution. Okay, the normal distribution is this top line, the blue one. It's the tallest, and then it's the shortest, skinniest. We have a little more margin of error, okay, when we're working with t-distributions. If you'll notice, as the sample size gets smaller and smaller, the peak is shorter, and then that makes it a little bit wider, okay? Or if you're working with t-distributions, as your sample size gets larger, it goes from 5 to 15 to 25 or whatever, it would get closer to the normal distribution shape, okay? The guy who gets credit for doing this, he actually, interestingly enough, worked for the Guinness Beer Company. And normally, if you make a big discovery, they name it after you. Well, since he was working for them, they couldn't name it after him. They would have had to name it after the Guinness Beer Company. We could have the, Guinness distribution or something. And they decided not to take part in that. So the guy just said, okay, well, we'll just call it student T distribution. So that's where that name comes from. Very similar to z-scores. This score ought to remind you a lot of z-scores, except instead of dividing by the standard deviation, they're dividing by the standard deviation divided by the square root of the sample size. Hopefully that reminds you a lot of the central limit theorem that we did in our last chapter. And it should, because that's what's happening here, is all these different little samples are going to be different from each other and different from the whole population. It's a sampling distribution of the sample mean. It's an SDSM. So that's why this is not the normal distribution, but it's very similar. Okay. So those are kind of those properties there. We kind of talked about them with our graph here. Requirements to use the t-distribution. The standard deviation is unknown, okay? And then either the population is normally distributed or your sample size is large enough. So if they tell you, hey, the average salary or the salary of the students is normally distributed, then you're good. You know you can use the t-distribution. If they don't tell you there's a normal distribution, then they need to tell you that your sample size is over 30. So if we surveyed only 25 students and it didn't come out to be a normally distributed, we would not be able to use the t-distribution with our calculator to build a confidence interval. But if our data is normally distributed, or if our sample size is over 30, then we're good. We can carry on, we can use a t-distribution in our calculator, and we can do just fine. Okay? All right, let's look at how that's going to work. In our calculator, okay, we mentioned those requirements already, okay, normally distributed or a large enough sample over 30. And again, your sample size can't be more than 5% of your population, okay. In our calculator, we'll go to Stat, we'll go to Test. In 9.1, when we did proportions, we arrowed down to option A, which was 1 prop z int, for one proportion doing intervals. This time, we are going to choose option 8, which says t interval. Okay, we're building a confidence interval, so interval is appropriate, but we're not using z-scores, we're using t's. Okay, on your formula chart, I tried to help you out with that. Okay, in our chapter 9 and 10 section, this time we're doing means, not proportions, we're doing means. Our confidence interval will be based on t interval. So that is the feature we are picking in our calculator. Okay, so stat, test, t interval. Okay, all right. When we get into hypothesis testing in chapter 10, we'll pick from these choices over here. Okay, once you tell it to do t interval, it needs to know whether you have raw data or you just have the statistics from the data. Okay. In this first example here, a study was conducted to estimate hospital costs for accident victims who wore seat belts. 20 randomly selected cases have a distribution that appears to be bell-shaped with a mean of 9,004 and a standard deviation of 5,629. Okay. Couple of things to notice there. Hospital costs for accident victims who wear seat belts. So in other words, if you're in a car accident and you're wearing a seat belt, okay, you went to the hospital for care, what was the cost of your bill? Okay, so they took 20 cases and they said, okay, these 20 people were wearing seat belts, they were in a car accident, they had to go to the hospital, the average of their bills came out to $9,004, the standard deviation was 5,629. Now what's interesting about this is all of these accident victims were wearing seat belts. If the accident victims had not been wearing seat belts, I suspect, I don't know, but I suspect that the cost would have been higher because they probably had more serious injuries and it costs more money for their care. Okay, I don't know that. That's just a hypothesis I have, but that's kind of what this problem is getting into. Now, I would point out, they have 20 cases. That is not over our magic number of 30. So the only way we can work this problem is if this data is normally distributed. They tell us it appears to be bell-shaped, so we're good. We either have to be told it's bell-shaped or we have to have more than 30 cases. We were told it's bell-shaped, so we're good. Okay. Now, in my calculator, I went to Stat, Test, and I picked option 8 for T interval. Okay. It needs to know whether I have raw data or just the stats. I have the stats. I do not have the actual hospital bills of these 20 people. So I don't have their data, I have their stats. So I'm going to choose stats. Make sure stats is highlighted. Okay, and then it says X bar. Well, X bar is the average. So what was the average cost for our patients here? 9,004. So my X bar is 9,004 that I'm going to type in. S, remember S is standard deviation. The standard deviation was 5629, so I'm going to fill that in right there. Okay. Again, these are from samples, so that's why we're using X bar and S. It's not a population, so it's not mu and sigma. Okay. Then they want N. Remember, N is your sample size. Well, how many people did we have in our survey? We had 20 people, so N is 20. And then they want the point estimate, and in part B, they want the confidence interval. Remember, instead of doing point estimate by hand, you can get the point estimate and your confidence interval at the same time. So same time in the calculator. Okay, I do need to tell it how confident I want to be. They say they want us to be 99% confident, so 0.99 is my confidence level, and I hit calculate. Now, because we're working with means, our point estimate is not p hat. Our point estimate is X bar. Okay? Our point estimate is 9,004. That means the average cost of our hospital victims is $9,004. Remember, when you're doing means, your point estimate is the mean. When you're doing proportions, your point estimate is a proportion, a p hat. When we're doing means, our point estimate is an X bar. And then the confidence interval. Confidence interval is 5403 up to 12605. That's our confidence interval. Okay. And then, yep, so that's it. Okay. And now they want a sentence to interpret it. Okay, well, what does this mean? Remember, our interpretation for confidence intervals is always we are whatever % confident. So we are, how confident were we? 99% confident. So we are 99% confident. Now, in the previous section, we would say that the true proportion of whatever. We're not going to say true proportion this time because this problem was not about proportions. This problem was about means. The averages, okay? So we're going to say we are 99% confident that the true mean, because that's what we found, the true mean hospital cost for all accident victims who wear a seatbelt is between these two numbers right here. And remember, this is dollars. Is between $5,403 and $12,605. Okay? Just interpreting this a little bit, thinking about it a little bit more. On our number line here, 9,004 is the middle. Okay? 9,004 is the middle. It could go as low as 5403 or as high as 12605. I shouldn't say it could go as high. We are 99% confident that the true mean is between this number and this number. Okay? So notice 5403 is below, 12605 is above. They don't ask this, but what if they wanted to know the margin of error? Okay, remember, margin of error is how much you're off by. So 12605 minus 9,004 is 3,601. And 9,004 minus 5403 is also 3,601. So our margin of error was $3,601. Okay, they don't ask us that. I just like to keep coming back to that. Okay, just for kind of thinking that through. Okay. All right, let's try another example here. In a study of the length of time that it takes students to earn a bachelor's degree is typically what we think of as a 4-year degree. Okay. Obviously, it takes some people more than 4 years. Okay, it took me 5 years, or actually 4.5 years. I know other people took 5, 6, 10 years. Okay, some people maybe get a lot of credits in high school or dual credit or something, and they may can finish in less. But typically, when we think of a bachelor's degree, that's that 4-year degree. Okay, so in a study of the length of time it takes students to earn a bachelor's degree, 80 students are randomly selected, and they are found to have a mean of 4.8 years and a standard deviation of 2.2 years. Okay, so the mean is 4.8. In our sample, in our survey, the average was 4.8 years. The standard deviation was 2.2 years. So S is 2.2. Okay, now notice there were 80 students in our survey. N is 80. Because that number is more than 30, it does not matter whether or not it was normally distributed. We don't care. Okay? We either need it to be normally distributed or we need more than 30. Since we had more than 30 people, we don't care if it's normally distributed or not, and they don't tell us if it was anyway. Okay? All right, so point A, construct a 95% confidence interval estimate of the mean amount of time it takes all students to earn a bachelor's degree, and then write a sentence to interpret it. Okay? All right, well, we know our N is 80, we know our X bar is 4.8, and our standard deviation is 2.2. Okay, so I'm going to go to Stat, Test. If you're not sure which feature to pick in your menu here, remember we're working with means and we're doing a confidence interval. So it reminds us, oh yeah, pick T int. So I'm going to arrow down to option 8, which is T interval. I have stats. I don't have the data, but I have stats. My mean was 4.8. That's my X bar. My standard deviation, or S, was 2.2. My number, my N, is 80. And then how confident did I want to be? They said 0.95. Okay. All right, so our confidence interval is 4.3104 up to 5.2896. Notice it repeats the mean and the standard deviation. Okay, sure enough, the mean is 4.8. It better be. That's what we told us it was. And the standard deviation was 2.2. It better be. That's what we told it it was. Okay, and then of course our N was 80. It repeats that. Okay. All right. Now, how do we interpret this? Well, anytime we do a confidence interval, we start out. We are 95% confident that the true, and now I got to start thinking. What did we find? Did we find means or proportions? We found means. What do we find the mean of? How long it takes people to finish a bachelor's degree. Okay, so we are 95% confident that the true mean amount of time it takes all students to finish a bachelor's degree is between 4.3104 years and 5.2896 years. Okay. All right. Now they want the point estimate and the margin of error. Remember, point estimates are always the number in the middle. Okay. Now in our case, we already knew the point estimate. We knew it was 4.8. But I would point out, so that's my X bar, okay? I would point out, if you did not know that it was 4.8, if you forgot that, point estimate's the number in the middle. So I could just average together 4.3104 and 5.2896, add them up, divide by 2, and that ought to give me my point estimate, the number in the middle. What would be halfway between those numbers, okay? And then our margin of error. Remember, margin of error is your E. Okay, well, on my number line here, 4.8 would be in the middle. I could add my margin of error, and that would put me at 5.2896. Or I could subtract the margin of error, and that would put me at 4.3104. So the margin of error is this distance. So 5.2896 minus the middle number, or the middle number minus the low number. Either way, I get that same E, that same 0.4896. So my margin of error is 0.4896. Okay, now just in terms of thinking about what this represents, the average bachelor's degree, according to the 80 students we surveyed, on average, it takes students 4.8 years. in order to allow for a little bit of margin for error, some are faster, some are slower, okay, we are 95% confident that the average amount of time is between 4.3 and 5.28. Notice that's more than 4 years. I just think that's interesting. Okay, we call it a 4-year degree, but the average time is above 4 that it's taking people to finish. And there's probably a lot of reasons for that. You know, compared to 20 or 30 years ago, more students are working while they're in school, I think. Sometimes students change their major and different things happen. So sometimes it takes them a little bit longer. Okay? I know it did for me. Okay, another example. The management at Disney World wants to estimate the mean waiting time, so average waiting time, at the Dumbo ride. They randomly select 14 riders and measure the amount of time in minutes that the riders spent waiting in line. The results are below. Assume the population is normally distributed. Construct a 90% confidence interval estimate for the true mean waiting time at the Dumbo ride and write a sentence. Okay, notice, how many do we have in our sample? We have 14. Okay, N is 14. That is below 30. Since it's below 30, we better be told somewhere that it's normally distributed. They tell us to assume that it's normally distributed. So we're good, okay? Now, if they had not put that sentence in there, we would not be able to work this problem because we have to know that it's normally distributed or our sample size is over 30. Our sample size was under 30. They told us to assume it's normal. Now, notice they did not tell us the mean and the standard deviation. So when I go to Stat, Test, and I'm still going to pick option 8 for T interval, okay? On your chart, we're doing confidence interval with means, so we pick T interval. That's what's on our chart. Confidence interval with means, we pick T interval. So that's what I'm picking. Up to this point, we've always chosen stats because we had the mean and we had the standard deviation. This time, we don't have the stats. We have the raw data, okay? But when I go to data, it says, okay, where is it? And it expects me to tell it the list where I put my data in. So I'm going to have to put this data in. And if I'd been planning ahead, I would have already done that, okay? But I was trying to show you all how that works. So I'm going to exit out. I don't have my data in there yet. I'm going to go to Stat, Edit, and I'm going to pick a list to put this data in. I'm just going to pick L1, but you could pick something different. So go up to L1, hit clear, arrow down, and it wipes it out. And I'm going to type in all of the numbers that they gave me. So 30, 29, 34, 41, type in all the numbers they gave. Ooh, that person only waited 16 minutes. That was fast. Okay, so I got all my data in there. Notice it's in L1. Now I'm ready to actually build my confidence interval. So I go to Stat, Test, option 8 for T interval. And now I say, hey, I've got data. It's not stats I have data. And press enter, and it wants to know, okay, where's your list? Where did you put the data so that the calculator can go in and find it? I put my data in L1. So I'm going to hit second and then the 1 key so that it will say L1 right there. My frequency, I'm just going to leave that as 1 because I typed every number in, okay? If there was a case where maybe you had 100 numbers and you didn't want to have to type them all in, and you could say, oh, 24 got used 3 times, and 27 got used once, and whatever, you might have put your frequencies in L2. Generally, that's not going to happen, okay? So I'm going to leave my frequency as 1, and then my confidence level. They wanted me to be 90% confident, so my confidence level is 0.9. Okay. Now, this is a little more interesting what it gives us here. All right, it says 23.334 up to 30.666. That's our confidence interval. Notice it says X bar is 27. So remember, that's our mean, okay? On average, the mean wait time for these riders at the Dumbo ride was 27 minutes. Now, we never knew that. They didn't tell us that up here. But I also didn't have to add them all up and divide by 14 because I knew that the T interval feature would give me that. It says, oh, by the way, just so you know, in addition to your interval, here's your mean. Your mean was 27, and your standard deviation was 7.746 or whatever you wanted to round to, okay? And notice it even lets me know, hey, your N was 14. You had 14 numbers. which is good. It lets me double check and make sure I didn't type in too many or too few numbers. Okay? Okay, so notice what this is saying is that on average, these 14 people waited 27 minutes. But the confidence interval, the 90% confidence interval, rather, was 23 to 30 minutes. Okay, so my interpretation, I am, or we are, 90% confident that the true mean wait time at the Dumbo ride is between 23.334 minutes and 30.666 minutes. Okay? That's the interpretation of our confidence interval there. If they had asked for a point estimate, remember if you're working with means, then your point estimate is an X bar, so it would have been 27. And if they had asked for a margin of error, then we could do 30.666 minus the 27, or 27 minus the 23.334. Either way, our margin of error would be about the 3.6 minutes. Okay? All right, so hopefully that helps you know how to work confidence interval problems with means as opposed to proportions like we did in 9.1.